Okay, part 3 of our lecture today, our class, which is assortativity. So we now will try to create a network where vaccinated and unvaccinated nodes are more likely or less likely to be connected to each other. So it's no longer completely random, right? We have two options of doing that. Either we will vaccinate, so we can create a network and then distribute nodes that are vaccinated or not vaccinated in a way that will actually look which nodes are connected. So that's one option. We actually have three ways of doing that. We actually have three ways of doing that. So one way of doing that is, like as I just said, we can create a network and then assign vaccinated status based on other connections of this node, so that if a node is connected to other nodes that are also vaccinated, it's more likely to be vaccinated. That's option one. Option two is to change the network creation algorithm. So it's like when in the Barabasi model we're attaching nodes to each other, not only we will attach more likely to nodes with higher degrees of distribution, so not only nodes with lots of friends will get new friends, but also nodes will become friends with each other only if they share their vaccination status. So we will first decide whether a node is going to be vaccinated or not, and then we will connect it to a vaccinated node or unvaccinated node with two different probabilities. But the third option is to start with all vaccinated nodes as one tight group, all unvaccinated nodes with another tight group and then destroy, shuffle them until we're happy with the level of disorder in the model. So which one to choose? I'm not actually sure. Let me see. So if we decide to change the network creation, then we just go down here to the network creation part. Where's the network? Here. And we assign nodes vaccinated or unvaccinated status, which will actually mean that, because right now we will have to move the initialization, because right now this whole vaccinated unvaccinated status, it's happening in the pandemic function. So we'll have to take it from the pandemic function, put it into the Barabasi network creation function, and then change the probability of connecting. Right now this is the probability of connecting, and we'll have to change it so that it's higher for nodes that share or lower if you want to make them anti-assortative, but so make it dependent on whether they share or don't share the property. Okay, so what's the other option? The other option would be to create a network, so we leave this part as is, but then when we drop properties on the node, so here in the network creation, instead of doing just rolling a die, tossing a coin, we will look at what's the deal with other nodes that are connected to this node. Is it a better way? Maybe actually, I kind of like it almost more. So both, well, maybe I should write that. So assortativity. 3 ways to actually create assortative networks. Assign status early on, then connect in the Barabasi model, depending depending not just on the degree, but also on status, either shared or either same, either shared with the new node or opposite. Right? The trick, like, okay, upside. What's the upside? Kind of nice to have all network creation together. Downside. Need to move the code from pandemic, which is like not too hard, but still extra work. More importantly, the network will no longer be Barabasi, strictly speaking. So it will still probably have the not clustering. It will still have the small world networkness, but it will be different. So, for example, it will probably become modular because two modules will emerge, right? Because people will be more likely to be connected within each groups, between these groups, which may be fine, but we just cannot call it Barabasi anymore, and whatever. Which also means that as we increase assortativity, there will be some either slight changes in the network. So it's actually a downside. It's kind of weird, but it's a downside. Okay, what other options do we have? Create a network, then assign vaccination status based on whether the node has vaccinated friends. Upside. What is the upside? The degree distribution will still match that, the degree distribution and modularity, even though we didn't talk about modularity much. I mean, we haven't measured it, but modularity. Okay, and other properties, such as modularity, will still match that of a Barabasi network. Downside, what are the downsides? The only downside I can see is that I'm not sure how to do it right now. Haha. So what do? We can, like, how do we do that? So when, instead of doing a uniform thingy, we can use choice. So we can sample, then we can choose, we can like sample different nodes with different probabilities. So every time we assign a node as a vaccinated node, we bump up probabilities of all nodes that are connected to it to be drawn at the next round, something like that. Yeah, I think I have an idea. Well, we can try that. Yeah, we can try that. Downside, I'm not sure whether there are any. Other option, create an ideally assortative or anti-assortative network, then randomize node status. Upside, real easy to do, and that's one upside. Another upside is that we can achieve 100% and minus 100%. We can achieve max and mean assortativity, because with other approaches, I'm actually not sure how to make the most assortative network possible. Like, we'll clearly be able to affect assortativity, but I'm not sure how to create the extremes. But with this model, we'll create the extreme deliberately, and then we will destroy it. So that's the upside. The downside, what are the downsides? The downside, it feels like it may be a little bit harder to control the amount of assortativity that we got. I'm not sure. Hard to control? But okay, let's park it. Before we do any of that, actually, we first need to make sure that we even can tell whether our network is assortative or anti-assortative. So let's do the following. First of all, let's take the initializer and make that we have in the pandemic thingy, in the pandemic function, and turn it into a separate new function because we will want to run it as we test that assortativity works. So let's take this entire thing. If initialize, if reinitialize, vaccinate G. Yeah. Yeah, okay, let's see. What did they copy? Okay, so there are actually two parts to it. One is vaccinating and another one making one node 6. So let's actually take this part but leave this part. So look, vaccination will become a new function, but finding the patient 0 will remain within the pandemic. Okay, and then we create a new function def vaccinate G, this part. So for node in nodes, what is nodes? Let's copy this thing. So nodes equals G get nodes. For node in nodes, if NP random uniform, yep. We don't have to return G, right? Because we just edited. So let's run this, let's run that. Nope, nothing works. And this is because vaccinate G doesn't work, and vax rate wasn't actually passed to it. Okay, so vaccinate G vax rate. We're never told vaccinate what the vax rate is. So let's do this like that. Yeah, it works. Good. So now with this vaccination thing, let's create the assortativity thing. So let's write a function that would actually assess assortativity. Def measure assortativity G. So how to measure assortativity? Assortativity is the probability that one way, well, there are several ways to define it, but let's go with the simplest thing that is like, let's look at the probability that two nodes are connected. No, let's look at the probability that nodes that are connected with an edge have the same property, either vaccinated in our case or susceptible. So if there is no assortativity, we'll have the value of 0.5 for the probability of being connected, right? Like a fair coin. If it's entirely, like, perfectly assortative, it will be 1. So all nodes that are connected share the type. And if it's perfectly anti-assortative, so most nodes that are vaccinated, like any vaccinated node has unvaccinated friends, any unvaccinated node has vaccinated friends, it will be 0. The probability that nodes that share an edge, that are connected with an edge, have the same status will be 0. So let's calculate that. So basically, we just need to go through all edges and count those edges where nodes match. So we can do that. Calculate the probability that connected nodes share the value. And we need, that's like one of the wisdoms of modeling and programming and coding in general. We start with a test. So we first write a measuring thingy, and then when we play with the actual creation of an assortative network, we will see whether our efforts lead to anything meaningful, because we'll be able to measure it. So measure assortativity for edge in G. What was that? there was some function that returns edges. Method get edges. Okay, get edges. For edge in G get edges. So now edge is an edge. It's a tuple of two values, one node and the other node. So if G values like the first node, which is like edge 0, equals G values edge 1, then count increase it by 1. So we need to initialize count to 0, and at the end we just return count, which is the number of edges where they matched, count divided by length, by the number of edges. Edges, actually we don't have edges, so edges equals G get edges, right? So we run G get edges, we take edges, the list of edges, we iterate through it, we compare. There was an error here for now, but okay, let's introduce a test here. Okay, actually like measure assortativity of a network let's create it. How do we create networks? Barabasi something, right? Create network, Barabasi of like 100. 1. Shouldn't be 1. Oh, it should be 1. Oh yeah, it should be 1. Stupid me, of course it should be 1, because all of them. Okay, change of mind. So G, because we haven't vaccinated them yet. Okay, so G, okay, so vaccinate G vex rate 0.5. Oh, it actually works. I thought it wouldn't, because values are actually tuples, where the first element of a tuple is a status and the second is this weird like number of days since infection. But I guess we initialize them as tuples, and so if the status is the same, then the tuples are also the same. So it actually works, even though it's weird. I would probably prefer to do it like that, like to reference the first element in both tuple. Remember, because when we create them, we like set them into, where do we create? Do we have like create node or something? Add node. Oh no, it's not here. It's in the, yeah. What? Oh yeah, here. I was staring at it literally, huh? Yeah, when we set them as vaccinated, we create a tuple. It's not even a tuple. It's not a tuple. It's a list, because I guess we want to change the second element of a list without changing the first. So we make them mutable. I remember that vaguely now was the case. Okay, so yeah, maybe we should only compare the first, like zeroth elements of both lists. So like, let's do this, but it doesn't change the way it works. So see, in this case, like the way it works right now, they kind of, we mostly get values around like 50%, because there is no rhyme and reason, because vaccination status is assigned randomly across all nodes, so nodes that are connected are not more or less likely to be vaccinated together or unvaccinated together. Good. So now we want a different thingy. So we want a vaccination rate. Let's go. Okay, let's give this thing some defaults. Vaccination rate equals 0 is the default. And another thing, assortativity. Assort. And by default, let's make it like what? 0, 0. So no assortativity. Preferential attachment. preference equals 0. Create, okay, vaccinate, distribute vaccination status. Okay, now we are ready to code that, and I have to finally make a choice. So look, Lord, so if we don't say it hard to control, maybe harder to code. Okay, you know what? So the third one, create an ideal distribution where they're really clustered together. I don't want to do that because I realized that I don't actually quite know how to code it. I first thought that I would like essentially run a mini disease of vaccination in the NS. Like I'll start with a node, then I will like vaccinate all of its nodes it's connected to until I get to the target number of nodes that are vaccinated. Now it's probably work. It would probably work. It would probably work. It won't be the maximum necessarily because it depends on it will depend on what node I pick as the first node. However, for anti-vaccination, it will be hard because like I need to pick a vaccinate node, then all of its friends will be unvaccinated, then all of their friends will be vaccinated, and that's just too hard. Should I do the second one, create a network then assign vaccination status whether a node has vaccinated friends? Okay, let's try to do that. Yeah, okay, let's do that. So let's do the following. Okay, so what should we do? We should now, so we start with assigning one node, right? Okay, first let's figure out how many nodes we need to vaccinate. I haven't done that actually. I haven't mapped it ahead of time, so I will be like coding it for the first time now. So nodes are 2n to vaccinate equals like g, like how many nodes are there? It's like length of g values, for example, either the dictionaries would work, multiplied by vaccination rate, and let's round it down to the closest integer. Yep, so number to vaccinate, good. Then let's introduce a probability to draw. So we'll be coding everything with this np numpy random choice function in mind, because with this function we can give it a list of nodes to draw from, and we can tell the probability of drawing each node. So we'll start with all nodes being equally probable, but then we'll look at nodes that are friends of vaccinated nodes, and we'll either bump their probability up or we'll reduce their probability down. Sounds good? Sounds good. Yep. Okay. So we code with this in mind. So P will be the probability, okay, prob will be the probability of drawing a node, and we initialize it with all probabilities equal, and P once how many nodes we have, all nodes, length g values, but probability is not 1, it's the probability we divided by length g values, right? Okay, now at this point I can continue coding, just hoping that I'm doing it right, but I actually like want to try that. So vaccinate, I want to write a test case. Test g equals Barabasi like 12. Vaccinate G, vaccinate, it doesn't work yet, right? I just want to do something. Vaccinate G. Okay, so for now, vaccinate G. Okay, for now nothing happens. So let's print probability. Print probability. Okay, 12 nodes was too fancy. 10 nodes. Okay, 0.1, 0.1, 0.1. Good. So we have the probability of drawing each node, and it's correct. Good. So now we don't no longer have this for node in n nodes. Let's actually let's comment all of that. Because now we do the following. We do for I in range n to vaccinate. So we'll just repeat the procedure as many times as we need to have the vaccinated nodes being vaccinated. That many times as the number of vaccinated nodes that we eventually want to have. And so we'll draw a node. Let's do that. I realized. Okay, we draw a node. Okay, so node equals np random choice from right now from the list of nodes that can be chosen. So what I realized is that we will want to not draw with repetition, which means, okay, sorry, let me finish the sentence first. Node random choice, so let's start with the range. How many nodes do we have? Len, okay, n nodes. You know what? Let's do n nodes because otherwise it's just really. Oh, nodes. Okay, nodes. Oh, len nodes. Let's do len nodes. Let's actually do len nodes here and here and here and range len nodes here. This is reasonably readable, so that's good. Yes, and we take from this range and we take with the probability of prob. Yep. And then this node will be vaccinated. Yes. So G values node equals, and let's make it vaccinated. That's how we make nodes vaccinated. All other nodes will stay healthy. Can I do gplot? Yay. Okay, good. PLT figure fixed size equals 5. Oops. PLT figure. Why is it so large? Okay, whatever. 3. Yeah. Okay, good. No, not good. Oh yeah, good, because we ran vaccinate with 0 probability of vaccination. Vax rate equals 0.5. Okay, so now something doesn't work. What doesn't work? Node equals np random choice range. Aha. Nope, I don't understand what's going on. Len nodes doesn't work. Because it says, look what it says. It says numpy float 24 object can be interpreted as an integer. And the mistake is, I mean, the error is caused by it happens in line 9. So does it mean that where should the integer be? Like the argument of range should be an integer. Is it true that the length of a numpy object is not an integer? print len nodes 10. Okay, another test. So a equals numpy. Wait, nodes equals g nodes. What is no, probability is the numpy thingy. Oh, I know. I haven't checked the syntax of this thing. So the syntax of this thing, probably the third argument is not the probability. The third argument is how many nodes, how many values to get. We only need one value. Nope. Oh, okay, good. Yeah, we have a different error. Different error is good news. So the previous error is gone, fixed. The truth value of an array with more than one element is ambiguous. Where does this come from? NP random choice where? What? Range? What? Range, lang, nodes. Okay, let's no. What? Probabilities? Okay, probably still the same thing. I shouldn't be lazy. I should just go and check how it's written. I mean, what the syntax of this thing is. Okay, what to take from? Size. Oh, replace. The third one is replace, and then only the fourth one is the probability. Okay, I have no words for myself. So replace, it doesn't matter, right? It doesn't matter. I can do like p equals like this. Nope. I can do p. I can use it as a, but I probably cannot. So size, what's happening? Oh. So size equals 1, p equals probability. Okay, unhashable type. Node is an NumPy array. Node. Okay, what is node? Nodes. I forgot what nodes are. Print nodes. Okay, nodes is fine. Oops, deleted wrong thing. So okay, what happens here? Unhashable type and p and d array. Unhashable, it means it can be used in an index of something. So node, for some reason, is a NumPy array instead of a number. Okay, so if I do print node, so yeah, see, I don't have a number. I have an array of length 1. So maybe I shouldn't say size at all. Maybe if I don't say size, yeah, okay. So like I should have learned it by now, right? It's not the first time I'm using it. Okay, so if you say size equals 1, it actually, instead of giving you one value, it gives you a length 1 list with one value in it, which is not what we need. So that's how you use it. I just wasted like 10 minutes of everyone's time. It's okay, it happens, like life happens, life is hard. Good, so now we have this thing. Are they getting vaccinated? Yes, they're getting vaccinated, they're great. I can delete this printy thingy. Okay, so what's our, now I spent so much effort doing that I forgot where we are. So right now, yeah, okay, right now is the default state and it's still the same as we had before. We sample randomly. We always sample through all possible nodes, so nothing actually prevents us from drawing the same node more than once. Which means that the share of nodes here is actually smaller than the expected share, because we might have attempted to color the same node gray twice. So we should actually, to make it work properly, we should change the list of nodes from which we draw. But also another problem is that if we shorten the list of nodes from which we draw, we should also shorten the list of probabilities. We can do that. Okay, let's do it in the following way. We can do it, right? Right. We're brave, we're smart, we can do things like that. Yay, yay. Right, nothing can stop us. We're not afraid of hardship. We won't turn away, we will do that. Let's do the following. So first of all, let's all probabilities be ones and not point ones. But now if I run it, it will give me an error. Because now probabilities do not sum to 1. But fear not, I will just divide by the sum of p, and p sum of p, because then p sum is faster than sum. So now, nope, didn't work. Oh, because it's not p, it's prob. Yep, now it works again. But now I no longer have to care about like whether my probability thing is actually sum to 1. I can just change them, and this thing will always work. So whatever is inside p will always, whatever is inside prob will always be transformed to probabilities with this operation, except if I create a negative element. I should make sure that they never become negative, because negative probabilities don't exist. So yeah, but they can be 0, they can be 1s. Yeah, I also don't want all of them to become 0, because then we'll have division by 0. But except for that, I can bump them in. For example, I can multiply them by 2 or by some coefficient. If I want to make some node to be more likely to be drawn, and I may divide it by the same coefficient if I want to decrease the chances of this node being drawn, right? Good, makes sense. So now let's introduce this coefficient, for now as a constant, like bump, boom, bumping coefficient, like preference, it should be above 1. So let's make it, okay, let's make it extreme. Should we make it extreme? Oh, we get preference as a, okay, preference equals 1. Okay, so preference will be our input. And if preference equals 1, it means that nothing changes. Let's add it here. Preference equals 1 means no preference, no assortativity. Good. So now let's go through it. So we picked a node, we set it as vaccinated. Now let's make all nodes. So we need to do two things. All nodes of this node that got all nodes of this node. What am I saying? All friends of this node need to be bumped up, and then this node should be removed from the list of nodes that can be drawn. So let's do it one by one. So first, for friend in gdict node, probability Okay, so we need to change the probability, but in order to change the probability, we need to be able to address it. But in order to address it, we need this thing not to be in NumPy arrange, but to be a dictionary, because we want to use nodes as keys. Sure, we can do that. So probability is no longer that. Probability is now a dictionary. Now, let's do the following. So for I in range len nodes, so for each node, no, for node in nodes, so for each node, probability of node equals 1. And we start with setting probability as empty dictionary. Now we can bump the probabilities up, but this thing won't work now because this is now a dictionary. So we'll have to return to this and fix that. But here we will do that. So probability of friend, which is a node connected to this node. Let's multiply it by preference. Right? Right. So that's part number 1. Done. Part number 1.5. This thing no longer works. Okay, so we need to, because probability is now a list. I mean, probability is now a dictionary, and we need a list or a NumPy object. Okay, so let's make a new variable called p, and every time at every run of the loop, we will update it. So for we will update it. For key value in prob items, because that's how we iterate through a dictionary, we will do p through a dictionary. We'll do p append probability key. Right? So we will iterate, and we start with p equals nothing, empty. So look, at every time we want to vaccinate a new node, no, every time we want to, every time we want to vaccinate a new node, we will recreate the list of probabilities. And we'll do it in the following way. We will initiate it as an empty, then we will iterate through the dictionary of probabilities, and we will append the probability for each key to the list of probabilities, because only list can go here. Only a list can go here. Now, another thing is that we shouldn't be drawing from the full list of nodes. This list should be shrinking as more and more nodes got vaccinated. So node list should be shrinking. We can try to shrink nodes. Is it okay if we shrink nodes? Yeah, let's do that. So we will shrink the list of nodes actually. Oh, okay. Look, so now it makes sense. Nodes will be shrinking, which means that here, let's do for node in nodes, we'll update probability of node. Yep. And then, so for node in nodes, we will, so nodes will keep the list of only those nodes we care about. We will remove nodes from this list, which means that if we iterate through items of this list, we'll always have only those probabilities that we care about. And it also means that the p value, this list of probabilities, will match the sequence of, and the number and the sequence of node keys in this list, because like we create p based on nodes. So just by design, it will match nodes, right? Now this is a new node. And to avoid clash of names, let's rename it it would have worked anyways, but it's just better this way. So this node is just something we use to iterate, same like here. And this is a new node. So this is a node that we are trying to vaccinate. Okay, now the last point, we need to remove the node we have just vaccinated from the list of nodes that can be vaccinated in the future. So when we do nodes, remove new node, right? It's not new node. Vaccinated node, like target node, target node, target node. Yeah, that's good. GG. Did I forget everything? Did I remember nothing? Let's run it. Okay, it seems to be running. So let's try vaccination rate of 1. Yay! All of them are vaccinated. Let's try vaccination rate of 0. Nay! Yay! None of them are vaccinated. Okay, so now did we actually do the preferential attachment? I think so. We haven't tested that, but look, we do bump probability up for nodes that are connected to vaccination nodes, or maybe down actually, if the preference is below 1, between 0 and 1. And okay, so it may actually work already. Let's try that. So let's do Barabasi of 20 nodes. And let's vaccinate 0.5, but with preference of 2, which means that like nodes that are vaccinated will tend to be together. Okay, can we see that? I think we can, huh? Don't you think so? I think gray nodes tend to form a subcluster. But you know what? We have a test. So we have a test. Where is the test? Measure assortativity. So yeah, let's actually have it above. It doesn't matter, but it's just more logical. So let's not just plot it, but also print, how is it called? Measure assortativity. Measure assortativity. Okay. Oh, all right. Yes. So look, in our measure assortativity thingy, the comparison of statuses didn't work. And why didn't it work? Because some of the statuses are wrong. And why are they wrong? Because we set nodes as vaccinated, but we never set, like we never copied this part. We never set some other nodes as healthy. So let's make sure that by the end of this entire part, any nodes that are still vacant nodes are set to healthy. So for node in nodes, it's like the remaining nodes. We do g values node equals this thing, right? So yay, now it works. Okay, so 0.56. That's not too good. Oh, but look, no, it's, well, 70. Let's set preference to 20. No, that's questionable. I'm not sure it works. Well, maybe the network is too small. Let's make 100. 67. Oh, look, we quite consistently get 67, which is not too high. So it seems to be working. What's the highest like preference? Basically, so by making the preference really high, I make it so that nodes that are friends of already vaccinated nodes are much more likely to be drawn. So basically, we're always drawing nodes. Maybe we're always drawing nodes that are friends of vaccinated nodes. Maybe that's just a natural limit for this type of a network. But we definitely can look at that. We can definitely go up to 0.65. Can I have Interesting. All right. So it's actually pretty hard to create extreme assortativity in a Barabasi network just because it's so connected. So even if all nodes that are vaccinated, say, belong to the same type, form a tight cluster, they still have lots of connections with the outside world. So they don't really form a bubble. To form a bubble, we would need to create a modular network where one module is like belongs to one type and the other one belongs to the other type. And I actually did it earlier when I practiced for this lecture. I did the opposite of what I did now. I first assigned the type and then I built the network. But like when I was writing these pluses and minuses, I somehow decided that that's a bad idea, this one, so I didn't do it. But with this approach, I could actually achieve assortativity of up to like 0.8 or something. And here I can only do 0.7, even that barely. Like 0.79, 0.69, 0.70 sometimes. Okay, what if we do preference equals like 0, which is the worst we can get? Oops, 0 doesn't work. 1%. Okay, so we can do the opposite. So we can do 70, we can also do 30. And this is like the stripy network. I'm not sure we can see that. Okay, we should be able to see it in a smaller network. So here, no, that's too small. So mostly, usually, see, it mostly goes like yes, no, or rather, no, yes, no, yes. Sometimes yes, no, yes. So it usually like changes the status from one to another. Okay. Well, that's what we got. Okay, let's roll with it for now because the time is late and everyone needs to go to bed or whatever, to have some tea. So good. Let's call it. We can create that like this. Let's now test the effect of this thingy on our network. So let's go down and we have this computational experiment. And this will be the first one, like the one that I have here now. It's called computational experiment. I forgot. It was computational experiment about what? About computational experiment vaccination rate. So now let's copy this. Oops. Ping CV. Now let's copy this entire thing and call it vaccination experiment, computational experiment, vaccination assortativity. Right? By the way, let's check whether this one, the previous one, still works. Because I changed stuff. Yeah, it still works. Good. Still works. Yay. Why am I doing that? Okay, look. Generate the plot. Come on. Okay, here's the plot. Good. Does this thing work? Yeah, this thing also works. Great. I didn't break anything. So this will be about vaccination assortativity. So what do we do? Basically, we go here to the pandemic. Oh, right now, pandemic doesn't know. So right now, pandemic actually calls vaccinate, and pandemic doesn't know anything about. So it gets the vax rate, but it doesn't get a preference. So preference equals 1. It will be another parameter. And when it calls vaccination, it will call it with a preference. Because we need to pass the parameter, right? And right now vaccination is called from pandemic, so we will send preference to vaccination, to pandemic, and it will send it to vaccination. Good. So now here we will do vax rate equals like what? Let's go with the highest, like the most interesting ever, which is 0.5. Okay, let's call it vax rate. But we'll set it as a constant here as 0.5. Why is it the most, like, that's the most diverse, right? The entropy is high, so like you can rearrange it in the most interesting ways. So, and but preference equals preference I param, and preference I param will be, now the preference can go from almost 0 to real high. So let's say, okay, you know what? Let's just create a list. So preference I param. Let's just make preferences a list. So n param steps will be equal to 5, and let's just write them explicitly. So we'll do 0.1. No, we'll do 0.1. We'll do 0.5. We'll do 1 for nothing. We'll do 2, and we'll do 10. Sounds good, because 0.5 is like, yeah, so that should be symmetrical. Preference. But then, what's the value of assortativity? Okay, so this should work, right? So, okay, preference, vaccination rate. It's almost good, except like I need to copy it here and here. And X label is like preference. Yes or no? I should have changed this to 10 for the troubleshooting part. Okay. Oh, okay, so it seems to be working, right? This part doesn't work. This legend is horrible. That's because it still gets vex rate, and it should get preference. Okay. So when preference is, I'm not sure what's going on. That's actually not what we got, what we need to have. When preference is high, they should all be friends with each other, which means that larger part of the population should be susceptible. Why the effect is so large? Do I have a mistake somewhere? Can I flash everything? Okay, let's do restart and run all. Just for my own sanity, okay? So the problem, one problem is that, like, even though we change preference, we don't actually know what happens with the assortativity. So we need to measure assortativity here and store it somewhere. What's taking so long? Which part is running now? What did I do? Kernel? I did restart and run all. Restart and run all cells. Okay, I think it ignored my command the first time around. Maybe not. What's taking so long? Where's the... Oh, I'm getting an error. Okay. And because of that, because vaccinate is not defined. Oh, that's because, okay, I'm really nice. I use vaccinate to test assortativity, and I use assortativity to test vaccinate. Okay, that's very helpful. Thank you. Thank you. So what? Okay, measure assortativity doesn't work. Okay, we cannot test measure assortativity. Good, fine. We can only test them together. Now we tested them, okay? So control that, run that. Here we want to only do 10 because we don't want to wait. And here we want to run this thing. Still same thing. And it's wrong. It's wrong. Why is it wrong? Because see, for some reason we have more. It's as if vaccination rate was still changing. But vaccination rate is not supposed to be changing. It's fixed. What the heck? How did it do that? Oh Lord. Okay, so let's. Should I measure? If I measure actual assortativity, will it help me? So I created a network. Then I called it pandemic. Pandemic did vaccination rate with vax rate. Should I how to test that? So and I cannot calculate assortativity because by the time it ran, I have more than one type of stages, right? Because I need, in order to get the correct assortativity, I need to calculate it immediately once it was initialized, but before the model was actually run. So it's like I don't want here in the pandemic thing. It's like I don't want vaccinate to be run. Okay, maybe that's what I do then. Change of mind. So I change, let's take vaccinate out of pandemic because it's better. So reinitialize, let's cancel that and that. And we just run it explicitly. So here I just run it like that, nothing works now. Oh yeah, because vax rate is no longer a thing. What? Oh yeah, because can no longer run. Vaccinate G 0.51. Okay, fixed. So now we need to vaccinate, otherwise pandemic doesn't work. Fine. So here as well, once G is created, we vaccinate G with vax rate. Oh, vax rate here is changing, so vaccinate rate. This is the legacy code, right? This is the previous task. Vaccinate rate with this thing, and preference is 1. It runs. Now here we create G. Now we vaccinate G with vax rate, and preference equals preference I per m. So remove this thing here. We remove it from this one, from this call, because it's no longer part of the pandemic. And then let's measure it. So we make it we need to store the assortativity. So measure assortativity. Is it how it was called? Measure assortativity? Yes, measure assortativity. So we need to measure assortativity of this newly vaccinated graph G, and we need to store it somewhere so that we could then look into it. For example, okay, let's assort history, which is not assorted history, but a history of assortativity. And the sort history will be also set to these beautiful zeros. So it's actually not just a sort history, it's a sort history of like I trial, I param, right? So we'll store it in the same shape of a structure as the total infected, which means that we can here, when we make instead of making, so when we make this second plot, instead of putting preference here, we can put averages. Oh Lord. NP average, so like we will do this thing, NP average of, but instead of total infected, we will do assort history. So we will use average assortativity as I broke something. Sort history, iTrial. So we'll use average assortativity instead of preference on this axis, except we need to do it not only for plot, not only for error bars, but for plot as well. Okay, so average assortativity, that's no longer presence, it's assortativity. So assortativity changes from 0.3 to 0.6, which is good. So, and with the middle at 0.5, this is good. The higher the assortativity, the lower the share of the population affected. And this is not good in the sense that I don't understand that. Because I always thought that if all unvaccinated people are friends, the pandemic should be worse, not better. Right? Why doesn't it work? Why is the total number so low? So right now the probability is 0.2. The infectious period is 5. Vaccination rate is 0.5. Vaccination rate is rather high, so let's do vaccination rate of low, because vaccination rate is right now around here. So let's make it 0.2. How's about that? Ew. Oh yeah, that's just dense of like noise. It's just noise. Let's just increase the number of trials and it will look better. It doesn't look better. Okay, all right. Wait. Why? What is happening? 1, 2, 3, 4, 5. Why now my assortativity values are worse? Some real weird thing is happening. Oh yeah, I removed the vaccination rate, so I reduced the vaccination rate. So now I can have, now my algorithm apparently doesn't work. I'm not sure why. Now as I increase the preference, can it be something is wrong? So either my algorithm is wrong, my measurement of assortativity cannot be wrong, it's too simple. So, well, everything can be, but so probably my vaccination is wrong, but what's wrong with my vaccination? Okay, let's actually test it visually. Let's test it visually with a really low rate of vaccination and preference of, uh-oh, it's not really low. Oh no, it is really low. Okay, let's test it with a really high rate of vaccination. Really high rate of vaccination and preference is highly negative. So right now they're supposed to be not friends with each other. Well, if I change it to 10, they're supposed to all be friends with. Okay, so everything is opposite, right? Ha 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 ha. When I make my preference 10, I thought they would form a cluster. But they actually seem to be forming not a cluster, but be all around the place, right? Maybe not. So this is how it works with preference 10. They're not friends with each other. This is how it works with preference point. It was 100, not 10. So now they are friends with each other. Yes, now they're friends with each other. So my code works in the opposite direction compared to how I wanted it to work. Well, now they're together. I'm just making sure I understand. Now they're not together. Okay, good. So when I multiply probability by preference, when preference is large, so I found a node and I looked through all nodes that are friends of this node, and I increased the probability of this friend by preference. So supposedly now it's a large number. Okay, let's just print probe. So, oh Lord. Yeah, so some of them are really large now. Okay, this is disgusting. Let's do 10. Still disgusting. But now some of them are large. Some of them are small. Okay, let's do not probe, but only those that are in the nodes. But yeah, we will have to use this comprehension. So, okay, which nodes are still there? Okay, let's do that. For node in nodes, print probe node and equals this thing, and so that it wouldn't create new rows. Then okay, so at first we got 10 10 blah blah. Why tens? Why are there? Oh yeah, because we already added one. So we added one, all of its friends became tens. Then it went like that. Then it went like that. Why? What am I missing? Probability. It's driving me insane. So probability is now 10 of friends of the existing node. Oh, wait, what? So vaccination rate is 0.9. Oh, Lord. Okay. Why am I so stupid? I interpreted it incorrectly. No, okay, everything works. Everything works. God. So vaccinated nodes are gray. So vaccinated nodes are actually all together. Everything works. Vaccinated nodes are all together. Look at that. When we have only 2 vaccinated nodes, no. They're not all together. 100. No, they're together. Okay, together, connected. Yeah, it works. If I do preference 0.01, disconnected, yay. Okay, so everything works. I can remove this printing thingy. Everything works. When I have a network with negative assortativity, all vaccinated nodes are far away from each other. When I have a network with very positive assortativity, all vaccinated nodes are together. Good. Why the heck then do I have these results? So let's include also here 0.01 and 100, and it will mean 7 parameter steps total. This is a disaster, but that's okay. All the assortativity values are close to each other, so maybe I need to go to vaccination rate 0.5 again. Probability network is weird. Okay, so now everything is sweet in the sense that we have this curve, but nodes with where vaccinated nodes are friends, networks that have vaccinated nodes as friends, I still have lower casualties. Is it just because the first node, because we pick the first node randomly, so sometimes we pick a vaccinated person so it can propagate? Because the patient 0 is always picked randomly, so if all vaccinated nodes are friends, then here with probability of 0.5% we'll pick, no, that's not true, but with probability of decent probability we'll pick a node that has no susceptible friends, so the probability won't be able, the disease won't be able to propagate. While here we will have, it will almost always have someone to infect. Yeah, I guess that's the case. Unfortunately, okay, what if I do vaccination rate of 0.9? Ew. The plot looks like ew. Do I have 10? I have 20 trials. Okay, do I dare to run? Okay, let's run a longer. Let's do vaccination rate of 80, which is like not 0.9, but still pretty high. So vaccination rate is pretty high. Let's see. And I'm running 100 experiments, so we'll have to wait a little bit. Okay, so when assortativity was for anti-assortative networks, population. I'm not sure I understand that. So I kind of came up with a theory, but that's a weird theory that, like, allegedly, because we pick the patient 0 randomly, if they are too clustered, then too often we pick a patient 0 without friends. That can be sick. And because the probability is so low. Okay, what about, let's pick the probability, actually herd immunity. So herd immunity here kicked in at approximately 0.6. Actually 0.5 was good. So 0.5 was at the cusp of herd immunity emerging. So 0.5 or 0.6 would be the most sensitive period then. So 0.5 was actually good vaccination rate for this particular. Do I keep the other things? So here probability was 0.2. Infection period was 5. Here probability is 0.2. Infectious period is 5. Yes, so supposedly that's the cusp of disease being able to propagate. All right, let's do a test. Let's do a test. Let's do a test what? Let's make sure that patient 0 is never vaccinated. So because if that's why I have this counterintuitive effect, that like in a world where all anti-vaxxers are friends, we still have fewer casualties, that maybe because I'm picking the patient 0 incorrectly. So let's go to the pandemic and make sure that patient 0 is susceptible. How to do that? So patient 0, let's like comment this one. Patient 0 equals, how to do that? I need a list of nodes that, okay, let's do a list of nodes. So possible, okay, susceptible equals empty for node in nodes if g values node 0, which is this where the status is stored. Oh Lord, if it is equal to healthy, then susceptible append node. So now by the end of this loop, susceptible will be a list of all nodes that can serve as a patient 0. So patient 0 equals np choice, no, np random choice susceptible. I think that's how it works. Okay, let's try it. So something, it seems to be working some way or another. Okay, let's try it here. Nope. 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 Why? Why doesn't it happily infect half the population? Now as half of the population is isolated. Why? What am I doing wrong? Preference. I tested this part already, right? I'm not doing it again. What else can be wrong? Okay, so there are two options. Either it's wrong or it's right. Either it's true and I just don't understand it. Or I have a typo. Some embarrassing typo somewhere that I also don't see. But now I'm actually calculating assortativity. I'm actually calculating it. Like I'm actually calculating it. Can the assortativity be wrong? Here, do I calculate? So here, okay, here assortativity is slightly below 0.5. Maybe assortativity is wrong. Can it be? Because here it's slightly below. So here they're all friends, the gray ones, but it's below 0.5. And here the assortativity, the preference is, oh my god, yeah, okay, the assortativity is nice, is wrong. Oh my god, so embarrassing. Look at that. It's wrong, right? 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 Because gray ones are the ones that are vaccinated, and here they are not friends of each other for the most part. Like these two are. Like, but look here, this is connected only to blue, this one is connected only to blue, this one is connected only to blue, this one is connected only to blue, and yet the assortativity is 70, which is more, so as if they were more likely to be connected. Okay, so something is seriously wrong here. Count is initialized to 0. Edges, G edges, for for age and edges, if G values H0 equals G values H1, why? I don't know. Okay, so G is now created. Let's work with this G. Measure assortativity G. Okay, edges, print edges. Yeah, so these are all the edges. Yeah, we have edges. Good. So edge 0. Okay. Okay, if this is true, let's print oh wait, maybe it works correctly. Wait, if my vaccinated nodes are not connected to each other, then they actually disrupt edges for more unvaccinated nodes. So more unvaccinated nodes are now connected to vaccinated nodes. So, but yeah, so the value should go down, not up. Why does it go up? So every time, healthy. Oh, look at that. All of them are healthy. So it actually doesn't notice those that... Look at that. I asked it to print the statuses. Ha 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 ha. Okay, at least we have a bug now. We found a bug. So I asked it to print status every time they match, but for some reason it doesn't do it for the vaccinated nodes. So let's look at this. G values, vaccinated 0, vaccinated 0. For some reason it doesn't do vaccinated. So why vaccinated? Ah, yeah, no, it's not a bug. It's not a bug. So right now, no, it's not a bug. So here everything, okay, no vaccinated guys are friends of each other. So all of them are healthy. And most of them are friends. Now, if I do it with 100, oops, oh yeah. Why now I have a larger value? Oh, now I have a smaller value. So now vaccinated. Healthy. Wait, it looks like it's real, but it's real in the weird way. It looks like it's real, but in a weird way. So what's happening is that when I make my nodes to form a tight cluster, they actually, my God, some network science is happening. They actually tend to be in the middle of the network. Why? So they disrupt it more, while when they are, oh God, when they are forced not to be friends with each other, then they are moved to the periphery. And that's because if I ask nodes that if every time I pick a node, oh God, right. If I, oh Lord, it's so weird. Look. If I, so it's an artifact of the way I created the network, but thank God. Okay, I finally, after 12 hours of suffering, I know what's happening. It's a mistake, but not a mistake. It's a wrong model, which is awesome. That's awesome. So look what happens. If I assign vaccinations based on friendship and not the other way around, I run into paradox. And that's a paradox of your friend having more friends. Remember that? I don't remember. I think we talked about that. Maybe we didn't. So your friend statistically has more friends than you, because you're more likely to be friends with popular people, with people who are like, because, okay, popular people have more friends. Did we have this discussion? So if we have a network like that, like we have a bunch of nodes, right? And you pick a person at random, and then from this person you go to another person, like you look at all of their friends. Look, if you pick a person at random, we'll pick popular and unpopular people, nodes, equally, right? But if we pick a person at random and then start to calculate their friends are more likely to include popular people. For example, for this person, this will be their friend is more popular. For this person will be their friend is more popular, right? So if we always, so basically the statement, that the fun statement is that on average your friend has more friends than you, because the probability that you are this person are rather small. Sorry. But you definitely have a friend with a ridiculous amount of friends that skews your average, like the average number of friends for your friends up. Bad sentence, but you got the point. Your friends are more popular than you, which is always true. But we did something like that in our network. So what happened is that if you pick the first person at random, like whatever, this node, and then you're saying, okay, then the friends of these nodes will now also be vaccinated, will share their status with it. This person is now promoted as being more likely as being vaccinated. So when I did positive preference, actually what happened is not only I made them like not only I made it more likely that vaccinated people would be friends, I also made it more likely that vaccinated people would be hub people. And then, so like at next point, I could have kind of contagiously made this person vaccinated. But now if you look at this network, actually a weird thing happens. It didn't become more assortative. It became less assortative, because now vaccinated people form this hub part and all unvaccinated people are on the periphery. And so if you calculate assortativity, it will actually be negative, because most nodes that are connected don't share the status, right? And the opposite happened when I used negative preference, because it's then if you have a network like that and they pick a person at random and I say, okay, this person is now vaccinated, and then I say, okay, but this person now won't be vaccinated, because I make the probability of picking it much lower, then the next person to be vaccinated will be always on the periphery. So when I made it, when I thought I would have alternation, actually what I did, I sent all unvaccinated people to the periphery. That's what's happening here, right? And because of that, all the bets were off. So both all the bets were off, and for lower vaccination rates, that's why I had this weird dance of death. So if I set vaccination rate to 1 and I like run the vaccination rate to 0.1, so 10%, and I run this network, and then I look at the levels of assortativity for different preference values. Okay, let it finish. Please finish already. Please do me a favor. Ah, yeah, that's why it's run so long. I have this weird branch here. Also traversed. Anyways, so this weirdness happens where the preference supposedly increases, but somehow the assortativity decreases. And that's why, because just my model is flawed. And my model is flawed because it's just a flawed model. And I didn't know that because obviously I decided to improvise at the last moment. When I was testing this lecture, I did this thing, I assigned status and then connected, and everything worked perfectly. And then I decided, oh, let me go for something better. And I created this thing, and this thing didn't work. And it was a horrible choice, and in a horrible choice in a non-obvious way. And I didn't realize that. And that's how I spent, how much now? 3 hours, 2 hours? In this strange thing that I'm recording. Good, good. Okay, so I'm out of steam. I cannot model this thing now for you. The interesting thing is that I have it modeled in my other notebook that's called Draft, where I use a different approach and where everything is different, and the assortativity is similar, but like healthy vaccinated is moved in the network creator, and the plot down there looks very reasonable and very predictable. And yeah, so I thought I would delete it, but now as I have two different variants, I will kind of publish this one as well, but I have no power in, like, I don't have like not time. Living force had left me, so I don't, I cannot explain to you how it works, but I will post it as an alternative reality, like multiverse version. So yeah, you are welcome to compare it. It is suddenly, it became an exercise in resilience. I hope you enjoy it. I doubt it, but I hope, but I doubt. But anyways, if you're really into this kind of thing, you're welcome to explore. Yay. Peace. Like, yeah, stay healthy. Good. See you later. That's all I can do for now. Bye.